Now, in this video, I'm going to explain a different rate law. This is the integrated rate law. The differential rate law showed the relationship between concentration and reaction rate. The integrated rate law shows the relationship between time and concentration. So if we show that comparison on a graph, we would have concentration on the y-axis and time on the x-axis, like you see that. If we were to plot out different concentrations at different times, we would have a zero order reaction that would be linear, and then a curved relationship for a first order and second order reaction. Now, if you're given concentration and time data, you can actually determine the reaction order by plotting several different graphs and determining which one creates a line, a straight line. And I'll show you all the different ways that we can plot graphs later on. Let's take a look at zero order reactions first. So for a zero order reaction, the rate is equal to the rate constant times the concentration to the 0th power. Now if we substitute in the actual definition for rate, which is the change in the concentration of a reactant over the change in time, we get the second equation. Now if we take the second equation and use some calculus to integrate it, now you don't have to know exactly how I did that and how that converts from that for the first equation down to this bottom equation, but you should know what the bottom equation is and what it represents. And the bottom equation is a way for us to calculate out the different concentrations at different times in a reaction. So the concentration A naught is the initial concentration. That's the starting concentration of this reaction. A with the sub T there is the concentration after an extended amount of time, maybe 50 seconds, 20 seconds, whatever amount of time you are looking at. And the negative K, the K, is the reaction constant, the rate constant, and the T is the amount of time that we want to look at this reaction, or the amount of time that goes by and when we are measuring this reaction. So if you take a look at this equation and you take a look at the graph, you might notice something peculiar about the two. They are related. Now that equation is the equation for that line on the graph. So doing that calculus allowed us to create an equation that represented a line, that represented pretty much anything you would need to know about concentration and time for this specific reaction at a specific temperature. That equation has the y equals mx plus b pattern to it that any equation of a line would have. So you can see here our slope is the m, negative k. The y-intercept is the beginning concentration, the starting concentration, and the x-intercept is that time. So this equation represents that line. Now, what if we have a first order reaction? A first order reaction has the rate law of rate equals K times concentration. And if we substitute in the definition of rate, we get the change in concentration over the change in time. And there's a negative in front of that because we're talking about reactants, not products for this. So if we take that second equation that I just put the arrow next to, and we use some calculus and we integrate the second equation, what we get is the natural log of the concentration at a given amount of time equals negative K times that amount of time plus the natural log of the initial concentration. What do you know? This equation also has the pattern y equals mx plus b, and it also represents a straight line with an equation and a slope and everything that a straight line should have. And all of these little parts represent things that we can measure and things that we can keep track of in the course of a reaction. We can relate any concentration and any amount of time as long as we know this equation. So if we plot a graph where the natural log of the concentration after a certain amount of time is on the y-axis and the time is on the x-axis, we'll get a straight line for a first order reaction. Now in a second order reaction, we have the rate law, rate equals K times the concentration squared. Now if we substitute in rate, we get negative change in or negative delta concentration over change in time equals K concentration of A squared. So we're just substituting in the definition for rate here. And if we use calculus and integrate the second equation here, we get 1 over the concentration after a certain amount of time equals K times T plus 1 over the initial concentration. Same exact thing here. We get a Y equals mx plus B pattern. So if we plot 1 over the concentration after a certain amount of time versus the time, we will get linear data with a slope equal to K, a slope equal to our reaction constant. And this line will allow us to figure out any amount of concentration at any period in time for this reaction. So let's try a practice problem. The data in the table to the right show the concentration of AB versus time for the decomposition reaction of AB to produce A plus B. So we have all of our time listed in seconds, 0 to 500 seconds, and different concentrations as the time goes by. So you can see the concentration of AB is decreasing over time, which is what we would expect to have in a reaction like this where we have a decomposition of AB. What we want to do is determine the order of the reaction and the value of the rate constant. And then we want to use that equation for the best fit line to predict the concentration of AB at 25 seconds, which is going to be somewhere in between 0 and 50. So we can make some predictions about that. Now what I've done here is I have entered all of my time data and my concentration data. And what I'm doing is I'm going to create a scatter plot. Now the first scatter plot that I'm going to create, I'm going to call that my zero order reaction. And this is just to see if I have a zero order reaction. So I put time on the x-axis and concentration on the y-axis. And I look at it, it is not a straight line, so we definitely don't have a zero order reaction. The next thing I want to do is I'm going to find the natural log of the concentrations. So I'm going to use Excel in all of its wonder to automatically calculate this for me, the natural log of all of that data, all of that concentration data. Now I'm going to reselect my new data and just edit that series. Now I'm going to call the series first, because this is what would happen if I have a first order reaction. I'm going to change the y values to the natural log of AB, that column. And guess what? I still get a curved line. This is not what I want. The last option is it could possibly be a second order reaction. So I'm going to plot 1 over AB, the concentration of AB. So I take the sum, parentheses 1 over what my concentration is, and then I expand that to all of the data there. And what I'm going to do then is I'm going to go back into my graph and reselect my data. I'm going to edit this and call this is a second order reaction, and change those y values, of course, and boom, I get a perfect straight line. This is definitely a second order reaction. And the information that I'm most interested in is the equation of that line. So I want that equation. Get that equation. Y equals 0.0225x plus 1.059. That will tell me all kinds of information pertaining to this reaction. So it says determine the order of the reaction. Well, based on my graph, the only graph that produced a straight line was a second order reaction graph, or plotting 1 over the concentration versus time. So this is a second order reaction. This is my equation. Y equals 0.0225x plus 1.059. This is my equation. Now, I want to predict the concentration of AB at 25 seconds. So if I look, it's going to be somewhere in between 0.950 and 0.459, but I don't know exactly where it's going to be. So I can kind of make a guess as to where it is, but I'm going to use this equation of this best fit line to calculate that. I'm going to substitute in the 25 seconds into that x, because remember, the x is the t. So y equals 0.0225 times 25 plus 1.059. And if I take that and equal it all out, 0.0225 times 25 plus 1.059 gives me 1.6215. So y equals 1.6215. By the way, the rate constant for this is 0.0225. That's K. So in case you're wondering the value of the rate constant, I guess I'm not explicit about it yet. So 1 over the concentration after a certain amount of time is equal to 1.6215. So I'm going to take the reciprocal of that, and the concentration is going to be equal to 0.61 with 2 significant digits. We'll put 3 significant digits on there. 0.617 molar solution of AB. And that is definitely right in between that 0.950 and that 0.459. So it makes sense that that would be the concentration after 25 seconds. And again, the rate constant is 0.0225 for my rate constant. Another practice question. The data in the table to the right show the concentration of N2O5 versus time for this another decomposition reaction. We're starting at time 0 and ending at 200. And we need to predict the concentration at 250 seconds. So this is even outside of the data points. This is extrapolation. So I have all my data entered in here. I even have my natural logs and my 1 over AB plotted. And actually that should be the N2O5, but I'm just doing this real quick here. I want to plot time on the x-axis and the concentration of my N2O5 on the y-axis, and I'm just seeing which one's going to give me that straight line. This one does not give me a straight line. It's a downward and it's curved line. So I'm going to reselect my data, and I'm going to change this now to a first order reaction just to keep track of what I'm plotting here. And I'm going to plot the natural log of the N2O5. And that's still, it kind of looks linear. Yeah, it's pretty linear. So I'm going to add a trend line. Yeah, it touches every dot. So we definitely have a line. And the equation for that line is y equals negative 0.0078x minus 0.0002. So that is the piece of information that I am most interested in. So I need to determine the order of the reaction and the value of the rate constant. Well, I got that nice perfect straight line where all the dots touch the line. I got that when I did my first order reaction plotting. And my equation is y equals negative 0.0078x minus 0.0002. So my rate constant, remember the rate constant is negative k. So the rate constant is actually 0.0078. So we have that the slope was negative k, so two negatives make a positive. So my k is 0.0078. Now I'm going to substitute in the 250 seconds, and I get y equals negative 0.0078 times 250 minus 0.0002. And I'm going to just keep multiplying all this out, and y is going to equal negative 1.9502. And remember, y is really the natural log of the concentration. So the natural log of the concentration is negative 1.9502. So if I'm solving for just the concentration, I need to do the inverse of the natural log. So I need to take e to the negative power of negative 1.9502, and that's going to equal 0.142 molar. Now, does this make sense? If I'm going past that 200 seconds mark to 250, it should be lower than the 0.210. So that makes perfect sense. Everything is working. So that's a good. Always make sure that your answers make sense. Now, one more practice problem. If we have the following reaction and we plot the natural log of A versus time, it gives us a straight line with a slope of negative 0.0045. This is a first order reaction. The rate constant is equal to 0.0045 seconds to the negative 1. It's a first order reaction, so that's the unit that we get for that. The rate law, it's going to be rate equals 0.0045 s to the negative 1 times the concentration of A to the power of 1, because it's a first order reaction. Now we're going to use that integrated rate law equation. If the initial concentration is 0.250 molar, what is the concentration after 225 seconds? So we're just plugging and chugging here. We're just putting in the information that we know and solving for that unknown. So the natural log of A, the concentration of A after a certain amount of time, after 225 seconds, is going to be equal to K, which is, or negative K, I should say, which is negative 0.0045 times the time, 225 seconds, plus the initial concentration, or the natural log, I should say, of the initial concentration. So ln 0.250. Now I can literally put all of this into a calculator, and what I end up with is negative 0.0045 times 225 plus natural log of 0.250. So negative 0.0045 times 225 is negative 1.0125, and then the natural log of 0.250 is negative 1.3863. I'm going to add those two numbers together, and I get negative 2.399. I'm just going to stop there. Negative 0.2399. And if I take e to the power of this, that gets rid of the natural log, and it gives me just my concentration. Then e to the negative 2.399 is equal to 0.0908. We'll stop there. 0.0908, 3 significant digits, molar solution of this A after a certain amount of time. So you don't even need to know the graph. If you're given information, that's enough. You can solve any problem relating the concentration with the time in a reaction, as long as you know that reaction order, 0, 1, 2.